Hi class, this is Dr. Nerz. This is your first video boost that is your own. Okay, first of all, I wanted to say everybody's been really quiet the last couple days in class, and I wanted to make sure that all of you feel that you can ask questions, because you can ask questions if I'm going too fast or if something I say doesn't make sense. Okay, so occasionally I'm going to make you your own video boosts, and video boosts are really just that, they're boosts. All right, we're a little behind schedule right now, and they're going to boost us a little bit. In regard to the schedule next week, I was a little unclear today. I was probably very unclear. And all of you have to come on Monday. But if you're a Tuesday, Thursday section, you should come on Tuesday and Thursday for your second part, the second part of the lab 4 and then the next lab. If you're in the Monday, Wednesday section, you need to come Monday, Wednesday, and Friday. And I know that's inconvenient, but after this week, you will not have lab on Friday. Okay? But we have some things we have to get done. There is an immense amount of material that has to be covered in only really what is about 4.5 weeks, and it is extremely tough to get through it all. And I like to do it with some depth. I don't like to just skim through everything. Okay, what I was going to do is a problem that would be a good review for your quiz. Okay, this is maybe a little harder. Is there a problem? Okay. So the first one, this is a nomenclature problem. This will kind of review where we're at with nomenclature. Okay. Can you see that?
Mm-hmm.
Okay, so we have a structure here to do. It has a double bond in the main chain and a double bond in the ring. In this particular case, I would probably choose the main chain, the straight chain, as the root name just because of the size of that chain. Okay, although I have to say it's a little questionable here. This is kind of a judgment call. All right, so what I'm going to choose is the longest continuous chain that has the double bond in it. And there's only one double bond. You can't include this double bond because this is part of a ring. Now, if you choose this as the center of your universe, you're going to have a very complex side chain. So I'm going to go this way. Okay? Now, the chain will involve 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, if I go this way, it's 1, 2, 4, 5, 6, 7, 8, 9. So it'll be this chain. That means it's a decene, okay? And we've been using the modern nomenclature. So using the modern nomenclature, that would place the double bond in the 1, 2, 3 position. I would number it this way to put the double bond in the lowest position. So I'm going to put the 3 here. Okay, so this is a dec3ene, or you could call it a 3-decene. All right, now what are these side chains going to be called? This group is going to be a 1, 2, so it's an ethyl. This is a bromo ethyl. Does it make a difference as to where that bromo is? Yes. So this is a 1-bromo ethyl. Okay? What other side chain do we have to name? We have to name this side chain. We're almost done already. Now this is a little weird because this is a cyclopentyl, but because it has a double bond in it, it's a cyclopentenyl. Okay? The way you would number this is this would be number 1, this would be number 2, and this would be number 3. Okay? So this is a 3-chloro, okay? Cyclo, I'm going to use the modern. I'm trying to stick with our resolve this semester to use the modern nomenclature. Cyclopen, enol. 1-enol. Now, do I need that numbering on that ring? That's a little questionable because it is a ring, all right? But I think because it's a complex side chain, I really need to state the position of that double bond, okay? That's a little bit dicey there, but I think that would be going too far to just assume it's in the number 1 position. All right, so putting this whole name together, what's going to come first in the name? This is going to come first in the name because of the B, and I'm going to start up here and work my way down here. It would be a, now what position is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this would be a 7, 1 in parentheses, bromo, ethyl, parenthesis, dash. Okay, where's the next group? At number 9? 9, dash, okay, parenthesis, 3, chloro, cyclo, I'm running out of room, uh-oh, pent, 1, enol, dash, I'm going to another line here, okay, this is in parentheses. What was our root name again? It was dec, 1, 2, 3, 3, ene. All right, so that's the whole name. That's a pretty long name. Now again, if you chose this as your root name, it's a little questionable. I went with this because it was bigger, and the side chains were a little less complex, although this is a fairly complex side chain. Okay, so what else do I want to do tonight? I want to talk a little bit about these kind of orbital drawings that we were working on today. So I made a different molecule to look at. It's kind of related. And when we come in tomorrow, very quickly we're going to go through this. We're going to spend just a few minutes on it because we are behind schedule. Okay, I'm not obsessed with my schedule, but I do get concerned about my schedule. We were doing pretty well for a while there, and then we got behind. All right, so say we had this. I'm going to show you how you could draw in all the hybridizations on this, or draw an orbital diagram. And I'm going to do it in red on top of this drawing. So what I'm going to do is draw an orbital diagram. Now again, what is an orbital diagram? It's where we are showing the orbitals using hybridization theory and linear combination of atomic orbital theory. We're showing where the orbitals are and what orbitals are involved. What's my time right now?
7:23.
Okay, so I only have a few more minutes, but let's see what we can do here. Okay, so the thing is, I'm going to draw in the lone pairs. This is similar to the one we're going to do in class tomorrow very quickly when we get in. All right. Yes, I know, your whole life is about organic chemistry. It's true. Okay, so what's the story here? Well, this oxygen would be assigned an sp2 hybridization because it has 2 lone pairs and 1 sigma bond. This carbon, sp2, 3 sigma bonds, no lone pairs. This would get an sp3 designation. sp3, why here? 2 sigma bonds, 2 lone pairs. Here, because there's an H there, it's sp3 because of 4 sigma bonds. This is sp2. This is sp2, sp3, sp3. Why? Because there's a hydrogen here. I don't want to draw bad geometry here, but there's 2 hydrogens there. This would be sp3. This is a little bit large, this molecule I picked. This would be sp3. Most of them are sp3. This one, we did this one in class. This is sp. This is sp for the nitrogen. Now again, this is using hybridization theory. Why sp here? 1 lone pair, 1 sigma bond. 2 sigma bonds. Okay? So what the hybridization is based on the number of lone pairs and the number of sigma bonds. Now, what I'm going to do is redraw this molecule without all those designations and start drawing the orbitals in. Let's see if I can do that in a couple minutes. I don't know, it might be tough. Let's see what happens here. Okay, so, all right, let's draw this. What did it look like? I'm going to draw it as big as I can. That's what I was saying in class. Draw it big. If you draw it big, you can fit the orbitals in, or you can see what's going on. Okay, so, yeah, I made this really big and complicated. Okay. This was the nitrile. The nitrile is one of the hardest ones to draw. Okay, I'm drawing all my lone pairs in green now. Okay, so my last designation was the the hybridization, but I'm going to draw all the H's in. Maybe, yeah, I'll draw the H's in. Okay, H here. Let's see how much of this I can get done. I can go beyond 10 minutes, so don't stop. Is it still running? Mm-hmm. Okay, so we were drawing these hybridizations in. So I'm going to start right here, right? These are all SP3s. SP3, this is how you would do it. It's kind of weird. Now again, the theory doesn't work very well for oxygen, so this is kind of a lame theory for oxygen, but it gives you the shape, which is a bent shape, okay? So this sp3 is going to overlap with an sp2. This will have 3 sp2s, sp2, 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 okay? So those are all the sp2s. This is an sp3, so this one's going to overlap with an sp3, sp3, and remember we said in class this is just going to be a 1s orbital for the hydrogen. We're showing the orbitals, there's another sp3 here, that are involved in the bonding, in the linear combination. So there's another sp3 here. So there's always 4 sp3s. This one here is an sp, 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 and this lone pair is in an sp orbital. Okay? And you could keep working along. I'm going to make this orbital bigger, this sp3. This is an sp3. I know they're not consistent in their size. sp3, sp3, sp3. This is going to be an s. Okay, this guy here has 2 lone pairs. So this would be sp3, 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 you get the idea. sp3. This is a 1s, okay? And you can slow these videos down and look at them a little slower. This is an sp3. You're like, oh yes, this has too much going on here. sp3, sp3, sp3. Why am I making that one sp3? Because it has 4 sigma bonds. Okay, 1s, 1s. We don't care about the hybridization of peripheral atoms because they're not central. They don't have a geometry associated with them. Okay, this is going to be sp3, sp3, sp3. We have a lot of sp3s in this molecule. A typical molecule would have a lot of sp3. This is an s, s. Now what is this one? This is not an sp3. This is an sp2. Ooh. This is an sp2 hanging out here. Okay, sp2, etc. All right, these are all sp2. These are 1s's. Okay, so we could just keep going there. All right, so those are all the hybrid orbitals. That's a lot of orbitals. Every one of those combinations is a linear combination. Now, what do you need to fill in on these? You need to fill in the pi bonds, and there are 3 places you have pi bonds. Okay, so in this case, which we're going to show this case tomorrow in class. All right, I'm just going to hone in on those pi bonds. Let me just erase this for a second. And it's very complex. But that is what I want you to do. That's what I mean when I say orbital diagram. Okay? So when you have this, carbonyl, all carbonyls will be the same, okay? As we said, this would be, I'm just going to show one of these because I think this video is getting to be too long. But right, you would make this sp2 for the carbon. And then what's left over? There's a p orbital. I'm just going to get my marker. There's a p orbital left over. And it would be in the front here. And then there would be a corresponding orbital in the back. So these are p orbitals making up the pi bond. Now the nitrile, we're going to do tomorrow in class. So try to do the nitrile. Try to fill in the pi orbitals on the nitrile. On the double bond that was just hanging off down here, okay, how would you draw the pi bond? The same way as this one, okay? So see if you can fill those pi bonds in. And again, tomorrow we'll work a little more on this. Okay, have a good night.